Hi, I'm Ellie Pinchers, the Education Officer here at the Royal Meteorological Society. In this series of short films, we're going to be covering some of the background information that teachers may find useful if they're teaching weather and climate at secondary level, and specifically if they're using our weather and climate teaching guide with accompanying classroom resources which can be found on our website MetLink. There's links to this in the text below. In this film, I'll be focusing on past climate change. The Earth's climate has always been changing, as some of the factors which control or force it change, and the climate system slowly responds. Ultimately, the Earth's climate is determined by the balance between the amount of energy we get from the Sun and the amount of energy the Earth loses back to space. If we get more energy than we lose, the Earth warms up, and if we lose more than we get, the Earth cools down. During the Quaternary Ice Age, which is the last 2.6 million years of Earth's history, global climate has been fluctuating between cold glacial periods and warmer interglacial periods, when the climate was similar to present day. The landscape that we see around us in Britain today has been moulded by these cycles of cold and warm environmental change. During the cold glacial phases of the Quaternary, a large ice sheet, the British-Irish ice sheet, extended across much of the British Isles. The landforms left behind by ice sheets allow us to reconstruct the former ice location and flow direction. Such landforms include depositional features such as moraines and erosional forms such as roches-montagneuses. The ice sheet depressed Scotland and the northern part of England. Its isostatic rebound from that is the reason why sea levels are rising slower in Scotland than in the south of the UK. We will look more at this in chapter 14. In the periods between glacial events, the interglacials, when ice had melted, temperatures in Britain were similar to the present-day interglacial known as the Holocene. In fact, during the previous interglacial, around 135,000 to 70,000 years ago, air temperatures were up to 2 degrees higher than the present day. In Britain, there is fossil evidence for species of elephant, lion, and hippopotamus frequenting the British landscape at that time. There have been 5 known ice ages in Earth's history. The present one is the Quaternary, as we said. The last glacial phase of the Quaternary, when large ice sheets spread across much of Europe and North America, ended approximately 11,700 years ago. There have been around 30 to 50 glacial to interglacial cycles in the Quaternary. All Quaternary glacial and interglacial phases, except the Holocene, are grouped together and known as the Pleistocene. The Earth's orbit around the Sun changes in 3 ways through time. These are known as the Milankovitch cycles. They do not affect how far away we are from the Sun on average through the year very much. This is a common misconception, but they do affect which regions of the Earth's surface are facing the Sun and therefore receiving the most concentrated energy from the Sun at different times of year. The 3 components are 1. Eccentricity. The combined gravitational pull of the Sun, Saturn, Jupiter and other planets cause the shape of the Earth's orbit to vary from its most elliptical to almost as circular. It has a 110,000 year timescale. The Earth is currently closer to the Sun in January than in July, meaning that the seasons are more extreme in the southern hemisphere than in the northern hemisphere. This means that in the northern hemisphere we receive about 7% less radiation in its summer and 7% more in its winter than the southern hemisphere in its equivalent seasons. Note that with a more elliptical orbit, the Earth passes closer to the Sun than it ever does on a more circular orbit. This can allow the melting of polar ice in the summer. With a more circular orbit, winter ice can survive the summer and grow the following winter. Number 2, tilt. The tilt or obliquity of the Earth varies over time on a 41,000 year cycle. If the Earth's axis were vertical, we wouldn't have any seasons at all. The same part of the Earth's surface would always be facing the Sun throughout the year. The more angled the axis, the more extreme the seasons. Currently, the Earth is tilted at 23.44 degrees from its orbital plane, which is halfway between its maximum and minimum value. The angle is currently decreasing. Number 3, precession. The angle also precesses or traces a circle in space on a 26,000 year time period. This is a gyroscopic motion due to the tidal forces exerted by the Sun and the Moon on the solid Earth, and associated with the fact that the Earth is not a perfect sphere, it has an equatorial bulge. It changes which star we see as the North Star. Currently it's Polaris, but about 13,000 years ago it would have been Vega. These processes have an impact on which part of the Earth's surface gets most energy through the year. If you have a look at a globe or a map of the world, you'll see that there is currently far more land in the northern hemisphere than in the southern hemisphere. As the way land and vegetation interact with the light and heat are very different to the way in which water does, this has an impact on the global climate. As the continents drift, these patterns change. Coupled with feedback mechanisms, for example, if a polar region receives less sunlight, it cools, allowing more ice to grow. This reflects more light, leading to further cooling. These three mechanisms can lead to significant changes in the Earth's climate, including the transition to and from ice ages. Another strong feedback mechanism is associated with the release of greenhouse gases from the ocean as the atmosphere warms, leading to further warming. The amount of energy arriving in summer at high latitudes determines whether the winter growth of the ice cap will recede or whether the climate will be precipitated into an ice age. There was a slow cooling of climate over the last 3 million years as polar ice sheets grew, partly in response to continental drift. At the mid-Pleistocene transition, around 1.2 million years ago to 700,000 years ago, the Milankovitch cycle started interacting differently, with a shift to a dominant 100,000 year climate signal. The planet has gradually cooled since the warmth of the Eocene, which was around 50 million years ago. This is associated with long-term geological processes slowly drawing down carbon dioxide out of the atmosphere. The cooling has not been smooth, however, with several transitions identified in the system caused by climate feedbacks, often involving the ice. First, Antarctica became glaciated around 35 million years ago. Then land ice became common in the northern hemisphere around 2.7 million years ago. Initially, the amount of ice in the northern hemisphere was driven by variations in the obliquity or tilt of the Earth's orbit, giving roughly 40,000 year long glacial cycles. Yet, as we entered into the past 1 million years, these cycles became visibly longer. Each of the past 8 glacial cycles has lasted around 100,000 years instead of the 40,000 years. The reason behind this shift is unclear and is an area of current research. It is clear that the size of the ice sheets in the more recent 100,000 year world are larger. Possible mechanisms for this are: 1. The ice moves more slowly over land because all the slippery soil has been worn away and left just bedrock underneath the ice sheets. It therefore builds up higher as less of it gets to the melting zone. Number 2. Unknown changes in the ocean circulation, probably in the Southern Ocean. Number 3. Changes in the dustiness of the atmosphere associated with the long-term shift in vegetation on land lead to changes in cloudiness and albedo, which is the amount of sun's light reflected back into space without warming the Earth's surface. The more electromagnetic radiation, light, UV, and heat the sun emits, the more energy arrives at the top of the atmosphere, or the higher the solar constant. The sun's output of electromagnetic radiation is linked to the level of sunspot activity. Even though sunspots are darker than the rest of the solar photosphere, the sun is actually slightly brighter, and the solar constant therefore slightly higher, when there are more sunspots. This is because the sun emits far more ultraviolet radiation and because of the other changes on the surface of the Earth. From a global perspective, the processes through which changes in incident solar radiation affect the temperature of the Earth's atmosphere and the climate at the surface are reasonably well understood. The spectral composition of the radiation is of crucial importance. For example, visible radiation reaches and warms the ocean and land surface. Ultraviolet radiation is absorbed by atmospheric oxygen and ozone, while water vapour and carbon dioxide absorb infrared radiation. The production and destruction of some gases, such as stratospheric ozone, also depend on solar ultraviolet radiation. However, the response of climate on regional scales to changes in the composition and intensity of incident solar radiation is more complex. This is an area of active research, and while significant progress has been made, definitive answers require further investigations into effects such as the role of stratospheric ozone, ocean-atmosphere interactions, and the role of clouds. Scientific observations of sunspots began after the invention of the telescope in 1610, and the approximately 11-year solar cycle, which can be seen clearly in this figure, was identified in 1843. Changes in the solar constant through this 11-year cycle are typically less than 0.1%. Note the y-axis scale on the graph, with an estimated global temperature response of less than 0.03 degrees C. Nevertheless, some correlation has been noted with droughts, temperature, ozone, etc., suggesting that there may be some feedback mechanisms. From 1645 to 1710, there were virtually no sunspots, a period known as the Maunder minimum. There has been no net increase in solar brightness since the 1970s, and the sun is currently in decline. Predictions for the next century suggest that there may continue to be a slight reduction in sunspot numbers. The warming seen from 1900 to 1950 was due to the combination of already increasing greenhouse gases and an increase in solar activity, and a lack of volcanic activity. The sun may have introduced an overall global warming, disregarding the 11-year cycle modulation, of approximately 0.07 degrees Celsius before 1960, but has had little effect since. The cooling in the 50s and 60s was due to aerosols. Other atmospheric pollutants which were being emitted, which were making it cloudier, reflected the sun's light. Clean air acts designed to reduce acid rain and improve air quality have started to reduce these, at least in Europe. Huge explosive volcanic eruptions in the tropics, energetic enough to push sulfur gases up into the relatively stable stratosphere where they condense into aerosols, can have a cooling effect on the climate by increasing the albedo of the atmosphere. More of the sun's light is reflected by the aerosols before it reaches the ground. The eruptions of Pinatubo in 1992 resulted in a global cooling of up to half a degree for a couple of years. Other recent energetic eruptions include El Chichon in 1982 and Agung in 1963, which were preceded by half a century of little volcanic activity. The combined eruptions of La Soufrière in 1812, Amayon in 1814, and Tambora in 1815 had catastrophic global effects, leading to a year with no summer in 1816, which amongst other things led to the Frankenstein's monster, Dracula, and the invention of formula baby milk. In the troposphere, the temperature mainly falls with height. Air rising through the troposphere cools at the adiabatic lapse rate, and as it cools can be either warmer or colder than the air around it. On the other hand, in the stratosphere, the temperature increases with height. This is because of the ozone in the ozone layer, which absorbs the sun's UV and re-emits this energy as heat, warming the stratosphere. This means that any air trying to rise from the troposphere, cooling as it rises, will always be colder than the surrounding air and will sink back to the troposphere. You can see from the shape of the cumulonimbus cloud at the top that air rising in the unstable troposphere reaches the top of the troposphere, the tropopause, and then can't rise into the stratosphere, so has to spread out sideways. Only very explosive volcanoes can blast material past the tropopause. If the volcanic material remains in the troposphere, it is fairly rapidly removed by rain. If it can get into the stratosphere, it has an impact for much longer. Eruptions that are mainly restricted to the troposphere are much less likely to alter climate for two main reasons. Firstly, the sulfur dioxide emitted by the volcano will not all be oxidised to sulfuric acid aerosols, as gas deposition processes operate on a similar timescale to oxidation. Secondly, the aerosol generated will be efficiently removed by deposition processes, and it will have a tropospheric lifetime of only days to weeks, compared to months to years in the stratosphere. If materials make it into the stratosphere, it gets caught up in the Brewer-Dobson circulation. Major eruptions in lower latitudes are more climatically effective as the aerosol is capable of reaching the higher latitudes of both hemispheres because of the direction of the Brewer-Dobson circulation. Material from major eruptions in the middle to high latitudes of each hemisphere tends to remain poleward of the eruption latitude. Major Icelandic or Alaskan eruptions therefore only influence the higher latitudes of the northern hemisphere. To affect global climate, a volcano should be explosive for material to reach the stratosphere and low latitude for the material to be spread through both hemispheres. Cooling is most pronounced over land regions because the thermal inertia is much smaller than over the oceans. In other words, it's quicker for them to heat up or cool down. As there is less land in the southern hemisphere, the cooling there is less than in the northern hemisphere, but lasts longer. The effects in the northern hemisphere are greatest in the summer because then the sun's radiation levels are at their maximum, and so increasing the reflectivity of the atmosphere will have the biggest effect. The crucial factor in determining the climate impact is not necessarily the magnitude of the eruption, but it's thought to be the quantity of sulfur dioxide injected into the stratosphere. Ash is removed from the atmosphere far faster than sulfur dioxide. A more dramatic change in albedo is associated with the snowball Earth hypothesis. It has been suggested that during the Proterozoic eon, 850 to 630 million years ago, the positive albedo feedback associated with ice accumulation led to ice covering the whole Earth. In this scenario, volcanoes and the huge amounts of greenhouse gases they emit would be necessary to break out of the ice climate feedback. Supervolcanoes are any volcano capable of producing a volcanic eruption with an ejecta mass greater than 10 to the power of 15 kilograms. For example, Yellowstone, 640,000 years ago, led to 5 degrees Celsius global cooling. Data from Antarctic ice, such as the Vostok ice core, show that carbon dioxide levels in the atmosphere and atmospheric temperatures fluctuate roughly together. The initial changes in temperature during interglacial periods are explained by the Milankovitch cycles. As ocean temperatures start to rise, the solubility of carbon dioxide in water decreases, and so the oceans release CO2 into the atmosphere. In turn, this release amplifies the warming trend, leading to yet more CO2 being released. This positive feedback is necessary to trigger the shifts between glacials and interglacials, as the effect of the Milankovitch cycles alone is too weak. Additional positive feedbacks which play an important role in this process include other greenhouse gases and changes in ice and vegetation patterns. The increase in carbon dioxide lags behind the increase in temperatures. However, in much more recent times, the changes in carbon dioxide concentrations in the atmosphere have preceded temperature increases. If there had been no anthropogenic impact on greenhouse gas concentrations in the atmosphere, the natural carbon dioxide levels had gone down to 240 parts per million. Then the Earth would be cooling to a glacial phase within the next 1500 years. Otherwise, if greenhouse gas levels didn't naturally get down that far, the next glacial would be in 50,000 years. However, with greenhouse gas levels as they currently are, without any further emissions, the next glacial won't come for around 100,000 years. Humans are significantly altering the planet, physically, chemically, and biologically. They are now a geological force that can control the evolution of climate. Earth's history is divided up into sections, partly according to the forces at play. Each section has a distinct marker. Anthropocene is the name of a proposed new section where humans dominate. In the next film, we'll be looking at air masses.